Hey kids, I'm back again for another video. Um, Here's our warm-up that goes with the lesson from yesterday about finding uh, local extrema. And make sure you see here, I am just asking you to classify, right? I don't need you to find heights. So identify any critical points on the interior of that domain and use the second derivative test, multivariable version, and I'm going to tell you what I got. I did get critical points of 0, 0, and that one was a saddle. I got 1, 1, and I got -1, -1, and 1, 1 was a local max or relative max, and -1, -1 was also a local max. I encourage you to put this into Desmos or GeoGebra or whatever and look at these 3D shapes because they're kind of cool, and to verify if you can tell, right? The saddle, that I can't make up my mind. Am I a, right? It's kind of like the patting the head and rubbing the belly thing. I can't decide if I'm a max or a min at that point, or if I'm a local turning point. All right. Okay. So as I said, in yesterday's video, we are now, this is this day 2 where we're going to take the local extrema and now talk about finding absolute, right? But it does have to be on a bounded region. So look at this picture here where, right, the domain is the XY plane, and that purpley thing is the 3D shape up there in space, but I've defined a bounded region here, a bounded region of that surface that could go on and on and on forever. But I'm looking just at this region, and I want to talk about absolute maxes or mins in there. So what does it have to do with the extreme value theorem? So remember from single variable calculus, the extreme value theorem, if we're just talking about the domain being the x-axis, right? If we closed an interval on the x-axis and said I'm going from, what is that, like -2 to 1, right? I am guaranteed by the extreme value theorem, as long as I have continuity, that I will have at least one absolute max and at least one absolute min, and those extrema could be at endpoints. Well, by existence, endpoints are extrema, right? Here, or on the interior. So calculus would find us any extrema candidates on the interior, and then the endpoints would just, by their mere existence, be extrema, and then we would have to just go back to the original function, to the height, to see who was the highest, who was the lowest. So we have a very similar thing in multivariable, right? Where for single variable, identify the interior candidates with calculus, look at the endpoints, and then look at the heights. And remember, the interior candidates come from when the first derivative is equal to 0 or does not exist. So in multivariable, our domain is going to be the XY plane, and there's the same image that I had on the intro slide. As long as I am continuous, so continuity, important, and I have a closed bounded set, then I am guaranteed that my z function, my f of xy, my height, I'm guaranteed to find at least one absolute max and at least one absolute min within that set. And those values, just like Calc 1, can occur on the interior of that piece of the surface or on the boundary, right? Either one. Just like here, the absolute max or min could have been at an endpoint or in the interior, right? All right, so just like before, think about the interior candidates where the partials do not exist or equal to 0 simultaneously. Boundaries. I included corners in boundaries because sometimes they get overlooked. They're basically the endpoints of boundaries, and I'll show you what I mean by that. So here's our steps. The steps for finding absolute extreme of a continuous function as long as I'm bound. Step 1, shocker. The calculus part. Find all the critical points within the bounded set. That's the calculus part. Partials simultaneously equal to 0, or if one of the other doesn't exist. And then plug that extreme value into your z, your f of x, y. Figure out your height. Where are you? Then find all the extrema on the boundary functions and determine the value or height. That takes a little bit of work. And there's calculus involved in that too, instead of just looking at endpoints, which there was no calculus in single variable. We're like, oh, there's the endpoint, there's the right endpoint. Make sure you don't ignore the corner points. Sometimes the corner points are like repetitious, but not all the time. And again, got to check the height. Then you just make a list of all your heights and compare. Who's the big winner for the max? Who's the big winner for the min? Good? All right, let's go. Oh, I do like to make write like a chart where I'm like on my, and I don't really organize it in a chart so much as much in my mind. Where are my critical points? How high are my critical points? What are my boundaries? The interior of that boundary. What, you know, on the boundaries. Where did I find those critical points? Plug the boundary points in there. And then any corner points, I'm also going to plug them in and see the height and then say who won. And the big winner is, drum roll. All right, so here we go. So maybe now you understand what I mean by boundaries. Look at those boundaries. If we are looking at the domain, right? I am looking at the domain that is restricted. It is bounded. This domain, now if I just asked you for the domain of f of x, y, there's no issues. The domain's all real numbers. But I only want you to use the domain from this square. From this square. So any x and y on the inside, any corner point, and any point on the borders or the boundary. Those are the only points, right, that we're going to consider our domain. So from our domain of all real numbers, we're shrinking it to this domain on the xy plane. We're only going to plug those points into f of xy, and we're going to get a piece of a surface up there. And on that piece, we're guaranteed to find at least one absolute max and at least one absolute min. Well, let's go find it. You ready? All right. Take the partial derivatives and set them equal to 0. So partial f with respect to x is what? 2x minus 4xy. And then the partial with respect to y, right? 8y minus 2x squared. Just like we did yesterday, create a system where those are both equal to 0. I'm going to take that first equation, factor 2x out, and get x is equal to 0 and y is equal to 1/2. So that's case 1 and case 2. Case 1, when x is 0, plug that into 8y minus 2x squared. Case 2, when y is equal to 1/2, plug that into 8y minus 2x squared and get me my candidates. So I have 3 candidates. Or do I? Right? Save yourself some work here. Remember, I have restricted the infinite domain to only points in that or on those boundaries or within that square. 0, 0 is in the square, right? It's right there. But is plus or minus 2, is when x is plus or minus root 2, is that in that square? I don't think so. Bye-bye, right? So I only have one interior critical point. 0, 0. I'm going to plug 0, 0 back up into my function and get what? 4, right? Only one critical point. It plugs 0, 0 back in and I get 4. So don't forget, we're going to do a lot of work around the boundaries. Don't forget that we have that original point already, right? We have one critical point with its height. All right, let's go to those boundaries. Critical points checked, right, from the inside. Oops. There we go. Check. Got that one. All right, so here we go with the boundaries. It's a nice little square, right? So I have the right boundary. Color that red. The white boundary, x is always 1 and y varies between -1 and 1. The left boundary, x is held constant at -1, y varies between -1 and 1. The top side, y is held at 1, where x varies between -1 and 1. And then the bottom is when y is held at -1 and goes between -1 and 1. So what I'm going to do is I'm going to attack that first side. I'm going to go 1, 2, 3, 4. So I'm going to start with that right line segment, and I'm going to go up to my height function. I'm going to say, what would this height function be if y was always, I'm sorry, if x was always 1? What would that look like? So do you see what I said? The boundary on the right in terms of y, because I'm going to hold x constant. And when I do that, here's all the heights I can get. So that's all the heights I can get by picking points all along that line segment. Now take its derivative, set it equal to 0, and do single variable calculus, right? Derivative is just 8y minus 2. That's 0 when x is a fourth. Then consider the bound, right? The endpoints of that line segment is when y is -1 and y is 1. So I got 3 candidates here. X is always 1 in all of these, right? Right, x was held to be 1. But on the interior of this boundary, when x was 1, y was a fourth. This is the height that I got. At the corners, I got a height of 11. At 1, -1, this boundary point, or this corner. And at 1, 1, when I took this corner up to the surface, I got a height of 7. Whew. All right. That's one side. Guess what we have to do? Oh, here, look, I drew, right, I highlighted them. Do you see? Those are the 3 candidates for my absolute maxes and mins. All right, now we'll go do the other side. So the left side, I'm going to do the same thing I did again. The boundary on the left, y varies, x is held at -1. So here's my height function. Here's my height function when x is held constant at -1. Take that derivative, set it equal to 0. I also got a fourth. Don't forget about its endpoints here. So hold x constant at -1, -1, -1. Here's the interior point. And then here's those 2 boundary points. 2 more. Oh, let me highlight them. There they are. They're the 3 candidates in my domain, right? They get sent up to the surface. All right, let's do the top. So this time, the boundary at the top is when y is held, right? So the boundary of the top, b sub t, when x varies and y is held at a constant 1, I just get this function. Take its derivative, set it equal to 0. And then remember, this has an unrestricted domain itself, so I have to cap it at these corners. Now I know we've already done those corners, but just for emphasis sake, right? At -1, 1, we get a height of 7. We saw that before. At 1, 1, we get a height of 7. We saw that before also when we did the boundary of this one. But the interior point, 0, 1, we got a height of 8. So there's my 3 candidates on the top. Now let's do the bottom, last one. Again, y is held constant, x varies. So we're going to write, how do we get the heights? When y is always -1, but x varies, then we'll take care of it only varying between -1 and 1 when we consider the corners. Took the derivative, also got 0. There's my corners. And there's my 3 candidates. Boom, boom, boom. All right, so obviously if you see you already had this height when you already tried a -1, 1, sure, you can leave it off. But I just like to always make sure I cover all my pieces. All right, so let's wrap it up. Compare all the values from the interior, but which we only had 1, remember? And then all the boundary corner points. So here they are. Right here was my 1 interior, and then around my boundary, I had all of these candidates. Compare their heights, right? Because that's down on 2D. They all look flat, but now take the function, plug them each into the function, and send them up to the surface and see how high they are, and then pick your winner. Who's the lowest? Winner. Who's the highest? 2 winners. Pretty cool, right? So those were my winners. All the others had to go home. Don't forget to state what your answer is. I have an absolute max is 11. That's the value. The height is 11, and there's 2 domain values that give me that height of 11. And then my minimum is at 4, and there's only 1 domain pair that gives me my minimum. Here's the picture that if you click on this PowerPoint and Canvas, you can explore that in GeoGebra, but hopefully you can kind of see here's 0, 0, right? You believe that that's the lowest. And then here's a height of 11 here at these 2 places. Right? Pretty cool. All right, that's how you do it. The combination of yesterday for the interior and then just adding the boundary pieces. So this problem was where you had 4 distinct boundaries. The next example is where my boundary doesn't have any corners because it's a circle. So here's my function that goes up, right? That takes all points from xy, from my xy plane, up to this surface that has no domain issues. But I'm saying I'm going to bound an area of that surface, a piece of that surface, a disk. And when you look down on the xy plane at that disk, you see this circle. There's the boundary, radius 4. You can use any point on that boundary, and you can use any point on the inside. Put it into that function, fxy, go up to the surface, and you're just going to get a disk, a piece of the entire surface. On that enclosed bounded air disk, I am guaranteed an absolute max and an absolute min. Let's go find it. So, shocker, step 1, took my partials. These are real nice. Everybody's linear. I make myself a nice little system. I do my algebra 1 super quick. And I get my critical point when x equals 0 and y is equal to 3. Didn't even have to solve the system, right? Don't forget to put that back into your function. Oh, first check, is 0, 3 in my, right? Is it in my region? Yes, it is. That is in my region. Plug it into the function, and I get a height of 9. But now when I consider the boundary, I don't have anything that I can fix, right? And remember what we did. We went up and we said, to, when we wrote our boundary functions, our job was to get it in terms of one variable, and we held one of the variables constant. Well, can we think if we can't do a constant, maybe we can just isolate x squared, right? And then at least we only have one variable. So I got the boundary in terms of one variable, solving for x squared, and then substituting that into my z equation, or my height. So x squared, I didn't want to get plus or minus. I just left it as x squared because I've got an x squared right there, right? So I'm going to make x squared have everything with y in it. That worked out well. So the boundary of my circle in terms of just y, here's x squared. I cleaned it up a little bit, and then there is my expression for plugging all values from the circle into my height equation, and only my values from my circle. And then remember, y can't, right? I have a radius of 4, so I can't go outside of there. So here we go. My boundaries in terms of y, right? I cleaned it up. And now what am I going to do? Yep. Know that y can only go between -4 and 4 because that's my radius of the circle, and take the derivative. Took the derivative with respect to, right, well, you know, just with respect to y, my single variable, and I got y is equal to 1. And then here's my endpoints, if you want, right? Endpoint, endpoint, and here was the interior point. Substitute those values into my, because I want to know the x that goes with that, right? So I'm not going to go and substitute those up into f of x, y. I only have a y. I need my x's, right? But remember, my x was equal to plus or minus 16 minus y squared. So I plugged -4 in, and I got 0. I plugged 1 in, and I got plus or minus root 15. I plugged 4 in, and I also got 0. So I took each one of those and plugged them in. Now that I have both an x and a y, now I went up and plugged into my height function, my z function. And with 0, -4, I got -40. Since I just had an x squared term, I got the same y value with both plus and minus root 15. Then I plugged in 0, 4, and I got 8. And who am I forgetting? All right. Can't forget the interior, way back at the beginning when we did the interior of the circle, not the boundary. We got our one critical point, 0,3, with a height of 9. Now who wins? Right, there's my lowest value, my lowest z value, and my highest z value. And there it is. Do you see the, right? It's kind of like that, like Pringles potato chip kind of like look, right? Here's my minimum at -40. Do you see that? And then I have 2 places where I have a height of 35. Cool. All right. So that is how we find our absolutes if we're given a bounded, you know, a closed and bounded surface, right? So thank you again for learning multivariable via video, and I will get this homework done, and then we just have one more video and one more lesson of the unit, and we're done with, or the chapter, and we're done with chapter 14. All right. I will see you. Bye.